Hello, students. And a couple of questions come in, so I'm going to go ahead and address those. This is out of section 3.2, so some questions on number 8, 13, 14, and then a couple of MCs. So let's take a look. We'll do some homework questions first. So 8A. So let's jump down here to 8A. It says set A is closed under addition and contains the numbers 2, 5, and 8. List 6 other elements that must be in set A. Okay, so it has to be closed under addition. So as I add these two numbers, I have to get a new number in the set. To be perfectly honest, there's infinitely many answers here. So when it says list 6, you just got to pick 6. So let's do a similar question. I realize that I think that's probably the best way to go so that you feel confident with them. So we'll jump up here. So what we're going to do is just right above it, we'll do a similar question. Let's do set B contains the elements, what do I want to say, a 3, a 4, and a 10? Sure, 3, 4, and 10. Okay, it has to have these in it. Now, there's more that can be in it. I just want you to tell me what else must be in there if it is closed under addition. So closed under addition. Okay. So if it's closed under addition, then if I take any elements from the set, for example, 3 plus 4, then that new number must be in the set. So that's one of my numbers. So now 7 has to be in the set, but also you'll notice 4 is in the set. So 4 plus 4 has to be in the set. So the number 8 must be in the set. 3 is in the set, so 3 plus 3 must be in the set. So that becomes now a 6, a 7, and an 8. Let's see here. A 3 is in there and a 6 is in there. So 3 plus 6 is 9. 3 plus 7 is in there. 3 plus 7 is 10. Oh, I already have 10. Oh, well. Whoops. And let's see here. What else? 3 plus 10, I guess. 13. So 1, 2, 3, 4, 5. There's 5. You could list as many as you want, but that's the idea. Set A contains the element 1. What other whole numbers must be in set A for it to be closed under addition? It's the same question then. So instead of giving you 3 numbers, what if I gave you 2 numbers? Like now, what else must be in the set to be closed under addition? So if I didn't tell you 10, I just said 3 and 4 are in the set. What else must be in there? Yeah, so that's kind of a good one there. What else? Yeah, I think that's about it. Because then I just take this away. So take 4 away. Now, what has to be in the set if I tell you that 3 is in the set? Well, if 3 is in the set, then 3 plus 3 must be in the set. And I already did 3 plus 3, so now 3 plus 6 must be in the set. And 3 plus 9 must be in the set. So I get this really nice connection. If I only know one element in there, then really I just end up with, as you can kind of see, all of the multiples of that number must be included in that set. I guess the reason I was pausing for a moment is there's another math problem that talks about if I give you, it's called a postage stamp problem. Uh, back when we used to have, when we didn't have forever stamps, they used to give a pretty famous problem. So they'd say, okay, so let's just say that you had postage stamps in 3 cents and 7 cents. That's only postage stamps you had, right? So what are the things that you could mail? And then they'd also ask you, what could you not mail? Okay, so you could not mail something that needed 1 cent because you couldn't, right? You couldn't mail it exactly, I guess I should say. If you put a 3-cent stamp on something that only needs 1 cent, you could still mail it. You just be kind of wasting a couple pennies. So 2 cents is out. 3 cents is good. 4 cents is out, right? 5 cents is out. 6 cents. Ooh, but I could put 2 3s on there. So 3 plus 3. So again, we're kind of talking about the closure property in this kind of sense. So 3 plus 3 would be 6. So now I know 6 is okay. 7, I've already got 7 over here. What about 8? So 3 plus 3 plus 3, or 3 plus 6 would be 9. So I know 9's okay. 3 plus 7 is 10, right? 7 plus 7 would be 14. 3 plus 10 would be 13. 3 plus 9 would be 12. Can I make an 11? Can I make an 8? So 8 I'm thinking about, and 11 I'm thinking about. And I don't think how I can make an 8. I need 7 plus 1, so I can't use a 7. And then 3 plus 3 plus, I can't use that. So again, over here, I need 8 cents I could not make. And can I make an 11 somehow? Let's see here. 3 plus 7 would be 10. So that isn't going to work. So I can't use a 7 with any 3s. So that's just 3. So no. So that's out. So there we go. So what you could say is you could mail basically from this point on, once you get a 12, a 13, a 14, and you have a 3-cent stamp, because then every thirds come in. 12 plus 3 is 15. 12 plus 13 is 16. 12 plus 14 is 17. And it just keeps cycling through. So basically, that's the biggest one that you cannot send is 11 cents. And that was a really cool problem. I think it was, for me, it was one of the few times that I got a chance to see how things like closure property could really start playing a role in solving other problems, which is, again, kind of a cool problem. Now, here comes the fun part. You could generalize this. I gave you a 3-cent and a 7-cent, but you could say, what if I have an A and a B? Right? So what's the biggest? And there's a really nice connection here between some of our properties. So 3 times 7 is 21, and 3 plus 7 is 10. And what's great is the biggest number that you cannot solve or cannot send is really a nice connection of those two. So in the end, the biggest one you could not send here would be an A times B minus A plus B. A really nice connection between what we do with these numbers. So again, that's a quick way, and that's for me, that's kind of pretty. So if they gave you a 5-cent stamp and a 7-cent stamp, then 5 times 7 would be 35, and 35, if I take away 7 plus 5, which would be 12, gives you 23, and that's Michael Jordan's number, and Michael Jordan is awesome. So that's it. So 23-cent stamp would be the 23-cent package would be the most I could have and not have the exact postage for it. Let's see here. Yeah, because you have 5. 5 plus 5 would give me 10. 5 plus 7 would give me 12. So 11 is out again. 12. Let's see here. 20, 24. So I could get 24. So 2 7s is 14. And I have 5 and a 5 is 10. So that's 24. So 24 does work. 25 would be 5 5. So that's 25. 26 is 3 7s and a 5. That's 21 plus 5 is 26. 27. Oh yeah, 4 5s gives me 20 plus a 7. That's 27. 28. 28 would be 4 7s. So that's 28. And again, now I have this beautiful string here of 5 consecutive numbers. If I take the number 5 and I add it to the first one, I get 29. I add it to the next one, I get 30, 31, 32, 33. So everything from this point on is going to be good to go. But I just can't make a 23. It's not a multiple of 5. So I want to subtract 5s until I get a multiple of 7. So if I take away 5, that gives me 18, not a multiple of 7. Take away another 5, gives me 13, not a multiple of 7. Take away another 5, gives me 8, which is not a multiple of 7. And that is a problem, which means 23 is the biggest number. So kind of a really cool connection there between the closure property and this. All right, so that takes care of question number 8. And let's see here. Next up was number 13. Let's take a look at number 13. 13, I think, is one where it says you got to put in your properties, right? So give reasons for the following steps. Yeah, so this looks pretty similar to A. So let's see here. Yeah, this one's pretty similar to A number 15. So if you're looking at A, the first step is just expanding. This is also sometimes referred to as place value expansion. So what you're doing is you're writing the place value of each digit. So you have three groups of 10 plus one. You have one group of 10 plus six. The next one is to take the 3 times 10 and the 6 and kind of switch those. I mean, that's really a nice idea. And this actually is two steps, because in order for these two to switch, that would be the commutative property. But you'll notice not only did they switch, really the grouping would have to change as well. So it is kind of the associative and commutative properties, because I could not take this entire group and this entire group and do that. So I'd have to regroup. So there's kind of an intermediate step. It looks like they've skipped it for some reason, but like you can't just switch these when they're inside parentheses necessarily. So anyway, so switching the order doesn't matter. That's the commutative property. Let's see here. Then what do we have here? One group of 10 and three groups of 10 is the same as 1 plus 3 groups of 10. So this is known as the distributive property of multiplication over addition. You've seen this in most of your other math classes. 3 times x plus 5 became 3x's plus 15. That's the distributive property. Same thing we're doing here. We just happen to have numbers everywhere. And so we factor out all the groups of 10. And yeah, then 1 plus 3 is just addition facts. 6 plus 1 is just addition facts. And then this would be kind of not expanding it, but condensing it or moving it back into place value notation. So those would be kind of the reasons for each of the steps. So each step does have a reason. So there we go. That takes care of, let's see here, 13. Next up is 14. Okay, so let's see here. 14, question 14 over in B. Looks like, yeah, so it looks very similar. Supply the reasons for the first couple steps. Yeah, so these look almost identical. They're just not in expanded form. So yeah, it does look like, what are we doing? We're changing the grouping. So if you change the grouping, that's reassociating. Then we change the order. Changing the order is commutativity. Changing the grouping again, which brings us back to associativity. Then we have addition facts and addition facts. So combining those objects together. Yeah, I think that's it. Okay. All right. Oops. Let's see here. Next one is an MC. Okay, well, let's jump in and try one of the MCs. I still love that question about somebody cooking a meal for Thanksgiving and he can only cook in his microwave oven. I love that one. It reminds me of my mom. Yeah, she would do something like that. Oh, I got a microwave. I can heat anything up in a microwave. No, not really. Not anything you actually want to eat, I guess I should say, right? Okay, let's take a look. MC number 2. Okay, so MC number 2. To find 9 plus 7, a student says she's thinking of this is equal to this plus this is equal to this plus this. What property or properties is she using? So again, very similar to the last couple questions, right? Think about which property did she use. If she regrouped, that's the associative property. If she changed the order, then we have commutativity. So I think that's it. So yeah, these are the only properties that she's using is associative or commutative, depending on which one you believe it is. And then, yeah, after that, it's just addition facts. 9 plus 1 is 10. There's no property for that. We could talk about a model if you wanted to, but it doesn't say that. It says this is just kind of how she's thinking about it. So in a sense, to use the model called compatible numbers, trying to make things like tens, that is actually utilizing one of the other components. We have to use the properties of addition in order to make that happen. Okay, and then there was one on group work. So the group work piece here was down here. Does the operation have an identity? And so, yeah, definition of identity is covered here in the text. I put it in the video. The idea of an identity is something you use with an operator and you maintain the exact same value. So for addition, the identity element, and you can look right above it up here. Let me grab my annotate tool. So take a look here. If I take any number, can I do this operation with one of the numbers in the top and end up with exactly the same thing I started with, which is the number 1? And well, probably most of you are like, wow, so you add 0 and you get back what you started with. Yes, but that makes 0 super amazing because no other number can I add to it and I remain kind of who I am. So if you look at this entire first column, it matches the number I'm adding. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and across we get exactly the same thing. So 0 is known as the identity for addition. This one in 2 is asking you, what is the identity for the triangle? So is there anything that I can triangle with something and get back to what I started with? Okay, that's what we're looking for. All right, let's see here. Okay. I think that was it. Yeah, there, that's it. So, I mean, when you think about it, even though I'm talking about addition right now, um, and we get to the next section with 3.3, and we'll realize that there is no identity element for subtraction, but there is um, when you think about multiplication. What can I multiply something by to end up with the same value I started with? And that is the multiplication identity element is the number 1. So anything times 1 gives you back itself. So those are things that, again, you probably knew before you came into the class. Maybe you just didn't know the name for it, but we kind of like the names for things. The names for things kind of help us link them together. So there you go. All right. Well, that's it for those. If you have other questions, please let me know. Otherwise, off you go.